Warming waters in the oceans. Hello friends, Jim here. Today's topic is ocean dynamics and their role in climate change and Arctic climate change. Now, in this talk, first of all, it's basically a talk that I gave for the MIR group a couple of weeks back. But it also is kind of a synthesis or pulling together of some major points I have been discussing in my videos over the past year or so. So kind of wanted to put it all together, kind of a summation, if you will, synthesis, as I said. So, the important role of oceans in controlling climate. You've heard me say it before many times that the oceans are the actual climate drivers. And that's because they have absorbed over 93% of heat energy generated from the burning of fossil fuels. So much heat has been absorbed by the oceans that we have a measurement, and it's called, you guessed it, ocean heat content, or OHC. So over the past 70 years or so, OHC is now estimated to be an accumulated more than 520 zettajoules of energy. And of course, as a reminder, the zetta prefix is a 10 to the 21 measurement. And of this 520 or so zettajoules, about 68% of that is trapped in the upper 500 to 700 meters. On the other hand, atmospheres have absorbed just 2%. And all the ice, sea ice, alpine ice, land ice, also approximately 2%. The rest has been absorbed by land, plus entropic loss to space. Because of this huge amount of energy absorbed by the oceans and their ability to store this energy, OHC, oceans are the main drivers of climate. So, where is the global warming going? So this is a specific breakdown. If you would add up all these values here, it adds up to 99.9%. The remaining 0.1% is lost to space. That's the entropic loss I alluded to a few moments ago. But as you can see here, oceans are the big enchilada. All these other guys here pale in comparison. The oceans have been saving our bacons until recently. And that's because as more and more heat gets absorbed, the oceans stratify. And then sequestration to depth is limited, is reduced. And we're seeing this. So how do the oceans absorb heat? You can do direct sunlight absorption if, big if, sea conditions are calm. And when you get to mid to high latitude, they're usually not. The tropics, yeah, the conditions can be calm there. But you have no productivity there in the tropics. And with all, because of where it's located, low latitude, there's always a direct sunlight there. You basically have almost a permanent thermocline year-round, which is why there's no productivity there and why the waters there tend to be clear. The main mechanism for how heat and gases become entrained in the ocean, mesoscale eddies. So, what is a mesoscale eddy? Typically, there are mini gyres on the scale of 100 kilometers or so in diameter. They can rotate either clockwise, anticyclonic, or counterclockwise cyclonic. And by the way, a clockwise rotation in the southern hemisphere is called cyclonic, and counterclockwise is anticyclonic in the southern hemisphere. But the mini gyres can spin either direction in either hemisphere because of how they pinch off the main gyre. And what are gyres? Gyres are rotating systems. You find them in the atmosphere and the oceans. In the oceans, they're a large scale, basically basin-wide, on the order of several hundred kilometers to over several thousand kilometers in diameter. And I did a very lengthy, deep, in-depth dive, detailed video discussing rotating systems. So if you're interested, type in rotating systems in the search box, and I go into all the nitty-gritty about gyres. So, you've probably seen me present this before, especially with talks with Sandy over at the Environmental Coffee House. This is the Gulf Stream, right? Yeah, here's Nova Scotia, Newfoundland, right? Eastern seaboard of North America. Here's the Gulf Stream coming across. Follow my cursor here. But you see this here? You see this here? You see this? You see this, right? All these little circular rotating bits that come off the main flow. These are mesoscale eddies. Got one right up here. Right? All these are mesoscale eddies. So the Gulf Stream is not this ribbon of water. It's this, I wouldn't call it exactly meandering, but you have the western intensification, which is clearly seen here. But as it makes its way across the basin, you start getting this pinch off. And that's due to balancing vorticity, pressure gradients, wind stress curl, Coriolis, all those parameters. As said, I discussed those in my rotating system video. So here's just a example of subtropical gyres and the associated ocean currents, because the ocean currents taken together will create the gyres. So for example, you got the Gulf Stream going up the eastern seaboard of North America, swings over, becomes the North Atlantic current, comes down the Canary, then the North Equatorial current, and you've got a gyre here. There's the North Atlantic drift that goes up this way, that branches off. That's where AMOC takes place. You see similar things in the South Atlantic, the Indian Oceans, the South Pacific, the North Pacific. You'll notice that if you look at the North Pacific gyres, the main ones here, they're rotating clockwise, right? Well, you're going to have a convergence zone in the middle, or a downwelling. Same thing here. And in the southern hemisphere, South Pacific, for example, the South Atlantic, they're rotating counterclockwise, but they still have a convergence zone in the middle because of the Coriolis. Coriolis deflecting to the left in the southern hemisphere, to the right in the northern hemisphere. So water piles up in the middle, and you get a downwelling. Now, those aren't the only gyres. You got these other little gyres here. For example, up here in the North Atlantic, in this little Norwegian current that does a little button hook. And then you have the Alaska current forming the Gulf of Alaska gyre. Now, these, if you look at the arrow direction, they're all counterclockwise, which means there is a divergence zone in the middle. You have upwelling. The upwelling brings nutrients. That's why the Gulf of Alaska has very productive biological productivity. And then you get some equatorial currents that ride right on the equator, and they're not acted upon by Coriolis. And the other reason why you get these gyres is because you have the land masses that help deflect, called topographic steering. And that's why when you get to the southern hemisphere, the southern ocean, the Antarctic circumpolar current, because there's no landmass at about 60 degrees southern latitude, it just rings around Antarctica. So, you can pause the video if you want to look at the names of these major currents, right? And of course, surface currents, are derived from wind, right? So they are derived from, the unequal distribution of solar input, to create a pressure and temperature differential and gradient that causes the atmosphere to move. If the movement is wind, it pushes on the water, called wind stress, and it induces the surface of the oceans to flow horizontally. So mesoscale eddies are often referred to as the weather system for the oceans. Due to their rotating nature, they can either move material from the atmosphere into the oceans or move material from the oceans to the atmosphere. As you've heard me say many, many times, oceans and atmosphere are a coupled system. In the northern hemisphere, if a gyre, mesoscale eddy, I'll refer to as ME from now on, if it rotates clockwise, and a cyclonic northern hemisphere, it has a convergence zone in the middle with a resultant downwelling. These convergent mesoscale eddy allow heat, energy, and gases to go into the ocean, to get mixed into the ocean. If, on the other hand, it rotates counterclockwise, cyclonic, then it has a divergence zone in the middle with the resulting upwelling. These divergent mesoscale eddies can move heat and gases back to the atmosphere. In the southern hemisphere, a gyro rotating clockwise has a divergence zone in the middle, and opposite for counterclockwise, convergence zone in the middle. And that's due to Coriolis effect. So, how do oceans distribute heat? Horizontal currents, right, induced by wind stress, arising from uneven heating of the Earth's surface from the sun, as I just described. Vertical currents, that is thermohaline currents, and they arise via differences in density, which is the result of differing temperatures and salt content, which we call salinity. You all know that. Denser water sitting over less dense water will sink vertically. Now, the movement of ocean waters to distribute heat is called ocean heat transport, OHT. So we can calculate that when we say, well, such and such a current or water mass is moving at so many sphere drops, and it has such and such a temperature profile. Well, we can calculate the amount of energy contained therein, and then we can say, well, the amount of energy being transported from region A to region B is so many joules, based on the heat energy content as well as the sphere drops. And remember, a sphere drop is 10 to the 6 or 1 million cubic meters of water moving past the point of reference per second. It does not convey velocity. It's a volumetric measure. You have also double diffusion processes. It's a complex process by which heat and salinity are mixed and distributed. Heat typically mixes at a faster rate. Diffusion to the atmosphere. Brine rejection during formation of sea ice helps create thermohaline currents, which is part of the double diffusion process. So what is double diffusion in the oceans? It is the solar heating warms the top, producing hot light, because you increase the temperature, it's going to expand, decreasing the density. And then you have underneath it salty or heavier water. right? Thermal expansion, higher evaporation rate. Heat diffuses faster than salt. This leads to an instability. The loss of heat increases the density, carries salty water downwards, producing an instability, a salt fountain. And this, by the way, is what happens traditionally with AMOC. Warm, salty waters from the Gulf of Mexico flow up to the North Atlantic, the Gulf Stream, and then becomes the North Atlantic Drift. It gives off its heat to the atmosphere, right? Diffuses the heat to the atmosphere. It cools down. Now you have cold, very salty water, very dense, and it sinks vertically. This process can also produce fingering, salt fingers, and establish layering, stratified layers separated by thin zones of turbulent mixing. And by the way, there's another phenomenon that's called internal waves in the oceans, and these are typically found at these boundary layers where you have some sort of cline, thermo, pycno, halo cline. You usually get an internal wave at the interface. Okay. So what impact does ocean heat content have? Thermohaline flow takes the heat and the CO2 to depth where they are sequestered. As oceans continue to warm, thermohaline flow slows. Sequestration to depth slows. This leads to increased heat building up in the upper water layers, and in turn leads to increased stratification in the ocean layers where the heat and the CO2 are now trapped in the upper layers. This trapped heat leads to increased sea surface temperatures and also diffuses to the atmosphere, increasing atmospheric temperatures. Right? Remember, 68% of that absorbed heat is trapped in that upper 500 to 700 meters, and it's getting shallower as the stratification increases. Increased stratification has major implications for net primary productivity, NPP. It is rapidly decreasing due to the nutrients not being mixed into the photic zone, which is detrimental for food webs. Where the stratification occurs, acts as a barrier preventing vertical mixing in the water column. So here's an example of when we see some, these are temperature here, so these will be isotherms, lines of equal temperature here. And you can see there's a, we're going from like 0, 500, 1,000, 1,500 meters, and so on. You can see here, if you look, these negative values here, this is 60 degrees southern latitude, 0 is the equator, so the positive values are the northern hemisphere, right? So, for example, if you look between, say, 30 and 20 degrees south latitude, you've got pretty much a homogeneous layer of water there. And then right about the equator, right, here's that almost year-long thermocline. We see a tightening here, very tight isotherms here, but look what happens when you get into the abyssal depths of the ocean. Very uniform here. We're talking, about 1,000 meters separating, from 1.2 to 1.1 for the potential temperature. But this is showing stratification. You will also notice when you get to the northern latitudes, up around 45, 50 degrees north latitude, around 50, 60 degrees southern latitude, what happens to the isotherms? They bend upwards to the surface. That helps bring nutrients in. It helps the productivity. Plus, a lot of it is a decline with the, say you have sea ice melting, you got cold water temperature there, and so forth. But there's a lot of information you can unpack from this figure here. Before we continue here, I just want to discuss something about sea surface temperatures and how it relates to when we measure sea surface temperatures. First of all, we have to keep in mind that when we see such figures such as this, how is that obtained? Lots of times it is via satellites flying overhead. And as they fly overhead, they aim the instruments at the surface, wait for the reflection, and get a reading. However, you can have different types of settings. You can have different apertures, different frequencies, and these all affect how the data is collected. Most often, the satellites are going to just read the skin of the water right at the air-water interface by using the appropriate aperture and frequency, which actually allows for a wider swatch of the ocean to be measured in a single pass. When we have those satellites that penetrate further down into the water column by adjusting the frequencies and the aperture, they can do so, but they sacrifice how much of the ocean they can measure in a single pass. In other words, the swatch will be much narrower. So there's a trade-off. Cover as much of the ocean as possible with a single pass, but get just the super skin, the very superficial reading, or try to get further down in the water column, but you're not able to cover as much of the ocean as possible. So those are trade-offs. Now, there's another little issue. When you read right at the surface, that can tend to bias the readings higher. What do I mean by that? When we measure air temperature, you see surface air temperature. Where is the thermometer placed? It's not placed right on the ground, because you put your hand right on the ground, especially if it's like concrete, asphalt, or bare ground, dirt, it's going to be really hot there as opposed to just, removed from the surface. That's because that's where the energy is hitting before it reflects, absorbs, and all that kind of stuff. So it hits there, a lot of it is absorbed, some of it's reflected, or re-radiated would be the correct term. So by convention, accepted practice, air surface temperature is measured at the 2-meter height. So where's sea surface temperature measured? Here's the kicker. There's no standard. It could be anywhere from right at the water-air interface to maybe a tenth of a millimeter down, a centimeter down, a meter down, 2 meters down, 20 meters down. There is no standard. I think they should be. I've long argued that since we use 2 meters for the atmosphere, perhaps we should consider using 2-meter depth in the oceans. Now, we can fill in this information here with buoys and Argo devices and ROVs. It's not just only satellites. Satellites are very convenient, and they can collect a lot of data for you in a quick flyover. But like anything else, you need other methods to complement, to enhance, to improve, increase our knowledge, our understanding. So I just wanted to point that out. And back to the video. Here is what's going on with the global stratification change in the upper 2,000 meters. So the stratification is giving as 10 to the minus 7 second per second. In other words, this is an acceleration. And we go from 1960 to about 2024. And this horizontal line at 0 is the annual mean. And what do we see here? We see in the last 10, 15 years or so, we see an acceleration. In other words, the intensification of the stratification is increasing. It's accelerating. It's not 0. Right? Just like, methane outgassing, temperature increases are all exponential or at least non-linear. Sea level rise is non-linear. Right? The stratification increasing is non-linear in the oceans, and this graph clearly shows it. So I can't go by without talking about the what's going on with the ocean heat content globally. This is from 0 to 2,000 meters. Now the scale is given as 10 to the 22 joules. Okay, so 10 to the 21 is would be a zettajoule. So this is 10 to the 22. So you can basically say, like for example, this would be 2.5 times 10 to the 23 joules. Or you can say 250 zettajoules. Right? But what do we see here? What? Increasing. Now, the blue line is the pentadal average. It's the 5-year average. Right? The black line is a yearly average, and then the red line is a 3-month average. So you can see the seasonal variations here. Then they smooth it out and so on. But we clearly see it's ever increasing. So when I talk about the 520 or so zettajoules accumulated, what I'm basically saying is go from, say, like 1990 to here and integrate under the curve. Right? When you integrate under the curve, it's an accumulated change. So even if you just wanted to simplify it and say, okay, this is a straight line, so you take the area of a triangle, you're going to find that you're going to get about 520 zettajoules. This is not a straight line. It's nonlinear, but that's where, when I say it's about 520 zettajoules, I'm basing it on doing an accumulated or an integration under the curve. Now you notice, here's about the mid-1990s, right? And you all know that I make the argument, I will continue to make the argument, that this is when the planet went past the tipping point. When the heat started accumulating in the oceans and started accumulating in the upper layers, no longer being sequestered either as efficiently to death, if at all. And of course, this is this is an update from Levitas, and this of course is Cheng et al.'s work here, and it was really interesting. With the exception of the Northwest Pacific, all the regions in the ocean are showing increased heat content. Mediterranean is really pronounced. And so basically, if you look at each of these little boxes here, right, like this box here corresponds to the North Pacific. This black box here goes to the Northwest Pacific, and so on. The dark blue box is the tropical Atlantic, etc. You feel free to pause the video and trace up the boxes to find out which, what's going on here. But as I said, Yeah, the Northwest Pacific almost looks like it's a cube root function. It's interesting that that region does not seem to be increasing, but the others do. But taken collectively, yeah, the oceans are just, absorbing so much heat. And you've seen me show you this before, but I'm going to keep showing it to you. This is, right? In my assessment, the planet overall went past a tipping point during the mid-1990s. Reason? Accumulation of ocean heat no longer sequestered to depth. And that starts diffusing to the atmosphere or starts moving horizontally to higher latitudes, both poles. And it starts working on the sea ice, cantilevered land ice, causing the sea ice to melt early in the year, freeze later in the year, more open water. Sea ice is not as thick. We're losing the multi-year ice. We're losing, the thickness, the extent, the volume. It's all decreasing. And by the way, the Mediterranean Sea, keep that in mind. And I know you know what I'm going with that. And you see me show you this before, but this is a 3D representation of the accumulated heat in the North Pacific down to 400 meters. Here it is. This is the anomaly. That's the temperature anomaly. Remember, specific heat of water is much, 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 much higher than air. This is a lot of heat. Right, you can see here's the Aleutian chain here, right? West Coast, there's Alaska, Kamchatka Peninsula, and so on. And then similar for the Atlantic, showing, you can see the influence of the Arctic waters here, like the Labrador Current. And here's Spain, right? Africa. Here's Gibraltar. Here's the Mediterranean signal, right here, and it gets down to intermediate depth. It's very warm water, but it's also very salty. So, due to buoyancy forces, it sinks until it finds its own buoyancy level based on similar densities, and that is about 700 to 1,000 meters of depth. But again, you can see all this warm water in the North Atlantic. So, Arctic warming. How is the Arctic warming? And it ain't just air temperatures. It's warming mainly through the inflow of warm ocean currents. There is an extension of the Kuroshio current in through the Bering Strait. This brings in warm water, and it's, by the way, the volume of this is increasing. Rebecca Woodgate's team and her research has been measuring this, bringing in the water is warmer, but it's also the flow rate, the amount of sphere drops is increasing, which means the heat content is increasing. And then there's the North Atlantic intermediate water. This is the main source of warm water into the Arctic. The NAIW originates in the Mediterranean Sea. And it's warming rapidly, right? Right here. Look at that, going right off. Now these units are 10 to the 9s, but still. Yeah, in joules there. So that hot water from the Mediterranean becomes the North Atlantic intermediate water, and thanks to Coriolis, it bends it and it makes a beeline right for Fram. Oops. So this heat is brought into the Arctic Ocean. It diffuses to the atmosphere, warms the waters, melts the ice. It's a major contributor to what is called the Atlantification of the Arctic. In other words, the properties of the water in the Arctic Ocean is becoming more and more like the Atlantic. higher temperature, higher salinity content. Ocean heat content is the main reason why oceans are warming. Surface layers are warming much higher than the deeper layers. Ocean heat content is a major reason why sea ice is melting and cantilevered land ice is melting, such as off Antarctica. So, here's a cross, and yeah, I pinched this from an exam I gave, but so anyway, so we have a cross section of water masses in the Atlantic Ocean. We have the depths given in kilometers from 1 to 6, and the equator. You can see the warm water from about minus 45 south latitude to about 50 north latitude or so, right? MIW, that's the Mediterranean Intermediate Water. There it is, right there. We see it right here. This little arrow going, that's aiming right for Fram. Some flows this way, but you get a bunch flowing this way. This downward arrow shows it's sinking due to buoyancy effect. Yes, it's very warm water, but it's also very salty. So this arrow is showing it's sinking to depth, which is in the 700 to 1,000 meter vicinity, and boom, a branch gets bent towards Fram. You have the Antarctic intermediate water. Here's the Antarctic bottom water. Remember that you also get deep water formation off Antarctica. And that's what this is. And it makes its way all the way up into the North Atlantic. Here is the formation of the North Atlantic deep water. Right here. So this is AMOC. Gives off its heat, it's cold and salty, it sinks, and it flows southerly. Interacting with other waters, little friction in parts, it heats up, it starts getting less dense, it starts rising, and where does it rise? In a vicinity called the Antarctic Divergence Zone, which, because it's bringing up nutrients, is the most productive open ocean waters on the planet. Most ocean productivity is coastal, due to upwelling and Ekman pumping and that sort of stuff. Not in the middle. So now as AMOC slows, this flow slows. The upwelling slows. The injection of nutrients slows. Productivity decreases. So what happens if you got less water flowing this way? Conservation of volume. You're going to have the Antarctic bottom water reaching further north. We are, by the way, seeing this sort of stuff. So here's an overview of what's going on in the Arctic Ocean. Here's the extension through the Bering Strait of the Kuroshio current, and it comes in and goes towards the Chukchi and the Beaufort Sea. Here is the North Atlantic Intermediate water coming in through Fram. Very warm water, and it basically, you got a little branch this way, but for the most part, it goes to the Eurasian side and circulates around here. Here is the Beaufort Gyre. Very important. So you got the East Siberian Sea, the Laptev, the Kara, the Barents Sea, right, so on and so forth. Svalbard, there's Novaya Zemlya. Okay, yep. So, you got all these, water movement here. And this dotted line is the average extent of the sea ice. And the average permanent extent. Wintertime it grows, and it then melts back in the summertime. Well, this is starting to shrink. So, as I say, we're losing the sea ice here. So, we got warm water coming in this way. We got warm water coming in this way. And we're losing the ice more rapidly on this side here because this water is warmer than the water coming in through the Bering. And I just like this one because it's kind of a 3D thingy, but it gives you an idea of the volume that the North Atlantic intermediate water brings in. Now you have the transpolar drift. This is where the Arctic dipole comes in, which I'm proud to say I was a part of in its discovery. And basically you have here a high pressure system that tends to sit over the North American side, and that rotates, follow the cursor, this way. On the Eurasian side, you have a low pressure system that rotates this way. So if you got something rotating this way, something rotating this way, it's going to grab whatever's on the surface of the ocean and push it. We'll just shove it this way. That includes sea ice. Now, depending on the configuration of these systems, the high and the low, along with what the Arctic Oscillation and to a smaller extent the North Atlantic Oscillation doing, they can work to either take the sea ice and either constrain it within the Arctic Ocean basin or shove it out through Fram, where it ends up in the North Atlantic. And then it melts. So, and now we're seeing, thanks to the work of my friend Igor Polyakov, finding that the Arctic dipole impacts the Arctic Ocean halocline. Here's that Pacific water inflow. And these little arrows, right, you see here, right, indicated here, that's upward heat flux. That's heat diffusing to the atmosphere, or if there's still ice, diffusing to melt the ice or prevent its formation. And a lot of atmospheric folks that they like measuring flux rates and get a watts per square meter. We can do the conversions. We can calculate the flux at the surface, at the air-water interface, but we typically measure the heat in the content, how many joules per cubic meters, and so on and so forth, and take a total of it. And so we can do the conversion, but we tend to report it the way we do. Now, due to limited budgets, everyone sending in proposals, fighting for budgets, trying to get money, trying to get time on a research vessel, and so forth. Our information is sparse as to flux rates. So it's incomplete knowledge. We need to do more research on it, but there are logistical problems associated with that. And now we have geopolitical issues also hampering our efforts on that, unfortunately. So what are the ramifications of Arctic warming? Warmer Arctic leads to warmer global temperatures. What happens in the Arctic does not stay in the Arctic. Ocean heat content moving in, all right, ocean heat transport, melt into sea ice. Sea ice melts early in the year, freezes late in the year. This leads to increasing open water time for the year, increasing from 5 to 7.5 months. And that means what? Albedo is decreasing. Right? Ice extent is decreasing. Ice thickness is decreasing. Ice volume is decreasing. Multi-year ice is decreasing. Heat diffusing to the atmosphere is changing precipitation patterns. I just posted a video about snow may be a thing of the past in the Arctic. Freezing rain is becoming more and more common. It is projected that snow will no longer occur by 2100. This affects regional and hemispheric weather patterns, including the Arctic dipole, the Arctic Oscillation, the North Atlantic Oscillation. And I did deep dives into each one of these oscillatory systems. In fact, I did deep dive into basically all the oscillatory systems of the planet. Did them a few years ago, but check them out if you're interested. So now we come to AMOC. Will it collapse or not? Now, I've discussed this with Sandy on Environmental Coffee House. And based on recent research I am seeing, the conditions at present indicate that it is unlikely to collapse. AMOC is definitely slowing down. There's no question about that. It is being measured. However, it is my assessment that it is not collapsing. Recent research indicates that for AMOC to collapse and stop, a massive influx, quote unquote, shock to the system of gargantuan amounts of fresh water in a very short time frame is required. Right now, yes, Greenland ice is melting and there's a lot of melting going on, but it's also that meltwater is actually getting entrained. And though the amounts are large, it is not the huge influx of water as the melting is meted out over time. And also due to the physics of the location, the entrained water is getting pushed over to the western Atlantic Ocean, or in other words, off the eastern seaboard of North America. So research has found that the way AMOC stops is when massive numbers of icebergs break off. And we're talking huge numbers of icebergs, like thousands, if not more. And they move off to lower latitude and then melt all at once in situ. This is the shock that will disrupt the Gulf Stream and bring AMOC to a stop. Thorium analyses support this hypothesis. I did about 4 videos discussing this, so you may want to check those out. As I said, I'm just kind of pulling together all these different, I guess, topics and threads I've discussed over the past year, 18 months or so, something like that, and just kind of like as a synthesis, having it all here in one spot. As more ice melts from Greenland, the possibility of having these large number of icebergs calving off decreases, thus reducing this possible scenario. Now, and we have the isotopic fractionation data that backs this up. About 13,000 years ago, Lake Agassiz in North America basically blew its accumulated freshwater lake. It just released it all at once, right into the North Atlantic. That was a massive shock to the system. AMOC stopped. Now, what I am concerned about, and you've heard me discuss this, is that there is a large amount of fresh water building up in the Beaufort Gyre, where conditions to change and conditions just align themselves just right. And what do I mean by that? The configuration of the Arctic dipole, the Arctic oscillation, and North Atlantic oscillation have to line up just right. If they would all line up there and this water gets released into the North Atlantic all at once, AMOC could stop. So in other words, here's the gyre here. If conditions happen and it goes this way, if it goes through the archipelago here, it's going to be physics. It's going to entrain it and so on. It's going to decrease what ends up in the North Atlantic. But if it releases and it goes right this way, yeah, depending on the volume, that could be the shock to the system that stops AMOC. The work of Wally Broecker, using radionuclides isotopic fractionation, has demonstrated the slowing, stopping, resumption of AMOC, as it's colloquially called, it's the conveyor belt, over the past 30,000 years. As you all know, I have great respect for Wally. He literally worked until the moment he died. They found him at his desk. But he is the grandfather of climate science. Now, if you had asked me 20, 25 years ago, would a stoppage of AMOC result in hemispheric cooling, I would have said yes. Today, my assessment is that instead of hemispheric cooling, you're going to get regional cooling. Why? All the global ocean heat content. The concern with AMOC slowing and stopping is, as I mentioned earlier, what happens in the Southern Ocean. You don't get that southerly flow to North Atlantic deep water. It doesn't upwell, bring in the nutrients. It can choke off, basically cause that food web there to end, or at least impacted adversely. So, this is just showing, right, here's the bottom water of Antarctica. Here's that deep water upwelling, right? Here, you see it right here. You got the divergent zone. It's going this way. It's going that way, right? That's the divergent zone. You got some wind blowing off the continent. Here's you see these purple arrows here. That's the circumpolar current. Lots of dynamics, physics going on here. But here's the upwelling. You got the water moving this way, the water moving that way. This is your divergent zone. And this is just the colloquial illustration of the conveyor belt, right? Gulf Stream flows up, water sinks, and you got a flow around Antarctica. You got a branch in the Indian Ocean, a branch to the Pacific Ocean, upwells, sinks, and so forth. Remember, all the major oceans, North and South Pacific, North and South Atlantic, Indian Ocean, and so on, and the Southern Ocean, it's really one big ocean. They're all connected. They all flow in somehow, these water masses, and by the way, the radionuclides, that's how we know we have water masses. There are certain signatures, not just a big pile of water. You have different water masses having different characteristics of, whatever chemical species, temperature, salinity, and they move. Horizontally, vertically, they move, they mix. And all these water masses eventually find their way and twirl around Antarctica. They come in, they move out. And so now come to a topic you've heard me discuss. And the reason why I'm including this here was that I was originally invited to talk to the Mirror group because they wanted to know why my assessment is that aerosol reduction has little to no effect on sea surface temperatures. that was the genesis for that talk there. And I said, well, I need to talk about all those other things here to lay the groundwork as to why I say this. So water has a higher heat capacity than air, 4 times higher. Ocean surface can be turbulent, reducing the energy uptake. The angle of incident decreases with an increase in latitude. As a result, not all incoming energy penetrates the ocean. And that's assuming you have a calm surface. If it's turbulent, which, like for example, North Atlantic usually is, that's even less in penetration of solar energy. What energy does penetrate quickly attenuates, following an exponential decay pattern. As a result, only the 1 to 2 upper meters of warm directly from sun energy penetration, unless in the tropics. Now, you can actually see some energy, you can see some visible light further down, but the warmth, the red wavelengths are quickly attenuated. Think of infrared, right? That's where the energy is. Though the energy is quickly attenuated. But you're going to get some penetration, but it's not going to contain much energy, not much heat energy. So I used to always chuckle at people, because I did a lot of scuba diving in my day, and I used to chuckle at people, wearing these bright red and bright orange wetsuits and so on and so forth. I'm like, dude, as soon as you go down like 2, 3, 5 meters there, it's all going to appear black. And you paid extra money for that? Anyway, so, yeah. Here's the other thing, though. If atmospheric scientists assess that reduction of aerosols will result in an atmospheric temperature increase of 0.42 C over 100 years, then with a higher specific heat of water and rapid attenuation of energy, it is not possible for aerosol reduction to have any significant impact on increasing SSTs. Certainly not the 5 to 7 C that I was seeing people, spouting off about. Thermodynamics informs us otherwise. It seemed to me that, I think Elliot Jacobson said this, is that the aerosol reduction was the latest climate crisis du jour, just like AMOC was. So we have to be careful that we stick to the science, stick to the data. Let's not get sensationalism involved, because that then only weakens what we present. We need to avoid becoming sensationalist about this. What's the data? What does the data tell us? What are the implications? Stick with that. We make better arguments. Temperatures keep increasing, both air and water, because humans continue to burn fossil fuels, adding more and more energy to the system. Yes, the ocean does absorb sunlight and energy, but it's the role of mesoscale eddies that help entrain this energy further in the water column, plus the role of thermohaline currents. Aerosols are a factor for increasing air temperatures, but not significant, if at all, for increasing sea surface temps. With reduction in thermohaline flow to depth and increasing stratification, the ocean heat content is diffusing upwards. That's helping to increase the sea surface temperature, and some of it continues to diffuse to the atmosphere, increasing atmospheric temperatures. All that ocean heat content, think of it as a big battery capacitor, storing energy, and now it's discharging that energy. And since it's not going as efficiently vertically downward, it's going to have to go somewhere else. So it moves sideways, horizontally, or vertically upwards. And that's what we see going on. So, aerosol reduction, and don't forget, and I'm going to bring up some other points right here, that why I say aerosol reduction is little to no impact at all. And this is just showing that when I talk about the angle of incidence of sunlight, okay, different parts of the Earth receive different amounts of solar radiation. This is because the sun's rays strike the Earth's surface most directly at the equator, right here. There it is, right? As you move away from the equator, the different areas receive different amounts of sunlight in different seasons. You notice how right here at the equator, it's concentrated. Then as you move up to, say, the tropics, right? Tropic Cancer, Tropic Capricorn, spreads out a little bit. But as you get to the high latitude, it's really spread out. Low angle. So you're taking whatever this amount of energy is here, it's concentrated, so when they heat up more, it's spread out more at higher latitude, so it's not going to heat as much. Basically, why it's cooler at higher latitudes. But now picture, the watts per square meter is reduced, and then try to, penetrate the ocean's surface with that. Not much is going to be impacting, and so the reduction of aerosol, maybe letting in more sunlight, it's really not going to impact. Okay? And where we see a lot of the aerosol hype is in the North Pacific, because of there's a lot of shipping traffic there, and they're burning diesel fuel that contains reduced sulfur content. But okay, here we have sun rays coming in. You have your, del, which is your declination angle. You have this is psi here for your latitude angle. This is your angle for longitude. But your declination here, the sunlight is coming in here. The surface is, this way. Here's your normal. This is your normal surface, right? This is the normal to the surface. It's at an angle here. So if this is your angle here, you take the cosine of whatever the value of this amount of energy coming in here, and that is what could be absorbed, assuming calm surface. So again, reduction of aerosol is not going to greatly impact sea surface temperature. What will impact sea surface temperature is what I have just been discussing for the last 5-10 minutes or so. It's the ocean heat content, the mesoscale eddies, and we're still continuing to burn fossil fuels. So, big but. And this is something you don't see atmospheric folks include, or at least the great majority. The role of marine phytoplankton, marine algae, and bacteria must be factored in. These organisms produce and release, you're going to love this one, this is a mouthful, dimethylsulfonylpropionate, DMSP for short, less of a mouthful, and dimethyl sulfide, DMS. By the way, DMSP reduces down to DMS. So dimethylsulfonylpropionate. These compounds are released into the atmosphere on the order of 10 to the 15 grams per year. These compounds are aerosols. Recent research shows that marine producers, by releasing DMSP and DMS, help regulate the planet's temperature and thus the climate. If the planet gets too warm, more DMSP is released. Too cold, less is released. In other words, the role of marine producers in releasing these groups of chemicals here is a negative or corrective feedback loop. They control the climate, the planet climate. Right? Ocean's a big place. They cover 70% of the surface. And don't forget, in addition to DMSP and DMS, phytoplankton release oxygen. 55 to 80% of atmospheric oxygen is from phytoplanktons. Also, sea salt spray are aerosols, and they're released in large quantities, typically via wave action. So this is like a coastal thing. Atmospheric scientists, what they do is energy in, so UV in, IR out, top of atmosphere, clouds, no clouds, watts per square meter, calculating EEI. Oh God, we're warming up because less aerosols. They're not doing a complete picture. Now, I will point out this concern of mine with the increasing stratification and the decreasing net primary productivity. The amount of DMSP and DMS is likely going to decrease. So this corrective mechanism might soon be lost. But it ain't reduction of aerosols. Don't forget, you have other sources of that. You got volcanic ash. You got other biogenic aerosol sources. The aerosols from burning of fuels is just one type of aerosols. There are others. And that kind of brings me to the end of this. So I hope you found this informative. I'm trying to do a big synthesis of various topics I've been talking about for the last year or so. I'm trying to wrap it up all together in one package with put a bow on it put a ribbon, a bow on it. What's the saying? Tie a ribbon, put a bow on it. Whatever. Okay, I don't wrap up many gifts. But anyway, yeah, all one-stop shopping, I guess you could call it. But so that's what's going on. And you've heard me discuss this before. What my concerns are, what my assessments are with respect to aerosols and AMOC. And we're seeing other issues. I just came across how the increasing acidity of the ocean is negatively impacting phytoplankton. Can't say that's a big surprise, but some quantitative studies being done on that. And the other thing is, like, why do the phytoplanktons release the DMSP and the DMS? The best hypothesis right now is that it's actually a stress response. They're responding to stresses induced in the environment they find themselves in. So that's the hypothesis that the researchers looking at this are putting forth. So, this wraps this up. Hope you found this informative. Please subscribe. Please consider supporting my work. You can join my YouTube community. You can buy me a coffee. You can become a patron over Patreon. All the info is in the description below. Share with your friends. Share on the social media platforms you use. And until then, you hang in there. And thank you for your time.